Hi, now we discuss something about diode circuits. So, a PN diode is obtained by diffusing P-type and N-type metal together, you can call. And because of the barrier effect, you can consider that a diode to be biased by the applied source. And a diode can be biased in two ways. One is forward bias, other one is reverse bias, you can call. So, this is the symbol for PN diode, So, symbol for PN diode. This is anode. This is a cathode, you can call. And this symbol indicates that a diode is a unidirectional device that allows the current only in one direction from anode to cathode. It do not allow the current in the reverse direction, that is from cathode to anode. Okay, so this diode to be biased in two ways. One is forward bias, other one is reverse bias, you can call. So in the case of forward bias, you say that anode is kept at positive potential with respect to cathode. This is the way of forward bias you say. In the case of forward bias, anode is maintained at a positive potential with respect to cathode. This is the case you can call anode, cathode you can call. Here anode to be applied at positive potential with respect to cathode, you say like this. So in this forward bias, you see this one now, the anode potential to be greater than cathode potential, you can call. Anode potential should be greater than what you can call means cathode potential, you say. Anode to be kept at a positive potential with respect to cathode. In this mode, the diode can allow the current and can act as a closed switch. In this mode, the diode can allow the current and can act as a closed switch, you can call. Right, where anode potential kept greater than cathode potential, you can call. And if you go for reverse bias, opposite to forward bias, you can call. In the case of reverse bias, the diode is operated with applied bias such that anode is at negative potential with respect to cathode, you can call like this, where anode kept at negative potential with respect to cathode, right? So here what you say means anode potential look like to be less than or equal to cathode potential. Anode potential look like to be less than or equal to cathode potential. Diode is in reverse bias, you can call. Ideally, no current flows in reverse bias where it can act as an open switch. Practically minority current flows, that to be negligible, you say. In reverse bias, the current flow is zero where it acts as an open switch. In forward bias, it allows the current act as a closed switch, you can call. And if you able to sketch the characteristics of this VA characteristics of this PN diode, that can come like this, you say now. Okay, if I draw the VA characteristics of this PN diode, you may get like this. This is the practical VA characteristic of a diode, you say. So whose VA characteristics would be like this, you can call. So this one now. So this is the VA characteristic of a diode. Plus V, minus V can call. So plus indicate for forward bias, minus indicate for reverse bias, you can call. Plus I, that is current in forward bias. Minus I, that is current in reverse bias, you can call. Commonly, reverse bias current is zero. Practically minority current flows, that is about microampere for germanium and an nanoampere for silicon diode, you say. So if I draw the VA characteristics of this diode in reverse, if I draw the VA characteristics of the diode in forward bias, ideally current starts immediately from 0 volt, but practically you say that the current can able to flow only after the applied voltage cross the barrier potential, you can call. Ideally the current starts immediately from 0. Practically the current starts once the applied voltage cross the cut-in voltage or barrier potential, you can call. See, so now this barrier potential or cut-in voltage, how much means around 0.3 volt for germanium and 0.7 volt for silicon, and this is due to the barrier effect across the junction, you say. So this is the VA characteristics of a diode under forward bias. So once the applied voltage across the cut-in voltage, the current in forward bias increasing exponentially, you can call, where the diode can act as a closed switch. This is the forward bias case, you can call. If I go for reverse bias, then the current ideally 0, practically a small minority current flows that is mainly dependent on temperature, you can call. So even this minority current flows there, diode commonly considers an open switch, you say. So in this mode, the diode practically considers an off switch. And it not only off in reverse bias, it will be off till in forward bias until this barrier potential you reach. So until this cut-in voltage or barrier potential you reach, it can act as an off switch. So this is purely due to barrier effect, you can call. So this is the forward bias condition, and this will be the reverse bias condition. Okay. So if I go for ideal diode, so this is the practical case I discussed. Just if you go for ideal diode, in the case of ideal diode, barrier effect is 0, you can call. In the case of ideal diode, the barrier effect should be 0 there, and the current conductivity starts immediately from 0 volt, you can call. So a diode said to be ideal if it acts as a perfectly closed switch in forward bias. So this one now, the ideal diode is considered to be what means perfectly closed switch in forward bias it is. Okay. So perfectly closed switch means R tends to 0. In forward bias, R tends to 0, you can call. And perfectly open switch in reverse bias. So perfectly open switch in reverse bias means R tends to infinity, you can call. Means according to the ideal condition, diode resistance ranging from 0 to infinite, it is of unlimited resistance. So for ideal diode, diode resistance is unlimited, and as well as for ideal diode, the barrier effect should be 0. So in the case of a practical diode, the diode resistance must be limited, you can call, due to barrier effect. For ideal diode, diode resistance should be unlimited, you can call. Suppose if I sketch the VA characteristics of an ideal diode, so that is a theoretical approach, what it comes means, check out this. Now I can able to draw the VA characteristics for ideal diode. This is the case. For ideal diode, I draw the VA characteristic graph now. So how much means, what is this one means, you see? So this is the VA characteristic for ideal diode, you can call. So you compare that one with the practical diode again. See, so now for the ideal diode, the current is maximum even at forward voltage 0. Even for 0 volt of forward bias, the current may reach its maximum, you can call like this. So even at 0 volt of forward bias, the current go to reach its maximum. That is because of barrier effect, you can call. So this is the case of forward bias. Come to the reverse bias. At any value of the reverse bias voltage, the current not flows, you can call. So the current should be 0 at any value of the reverse bias voltage like this. So whatever the value of reverse bias voltage, the current should not flow there. Current should be 0. So this is the case of reverse bias, you can call. See, so now what the resistance of the diode under forward bias condition means, that should look like be 0 there, that should look like be 0. Here if you go for this, R equal to V by I, So voltage 0, current is maximum, that to be 0 ohms. So in forward bias, the resistance will be 0. In reverse bias, you see this one now here, what is the resistance means? R equal to V by I, So whatever the voltage you apply, current should be 0 there. So for any value of reverse bias voltage, current 0, that should be infinite. So for ideal condition, the diode resistance must be 0 to infinity, you can call unlimited. If I go for practical diode, so because of the barrier effect, you can call, because of the barrier effect is there, the diode resistance must be limited, you can call. So up to certain potential, the current is not there, means some resistance is considered. And in reverse bias, the current is not 0, you can call. Some minority current flows means some maximum. So for a practical diode, resistance is minimum here. So resistance is minimum in this case. In this case, resistance should be minimum, right? here it is a minimum resistance you can call. Okay, here the resistance should be what you can call, sir, means minimum USI. So it is minimum resistance. Okay, resistance should be minimum, that is just a few ohms you can call. And if you go for reverse bias, because of some minority current is there, it's not be infinite you can call. Some this should be order of what means some mega ohms here. So in this case, R should be order of mega ohms you can call. So for practical diode, resistance is ranging from minimum to maximum. It is a limited one, not be unlimited you can call, right? So based on that, now I can able to examine what is the equivalent model of a diode, both for ideal condition and a practical condition. And so now for ideal condition, the diode resistance is unlimited and barrier effect is 0, I told. For a practical condition, barrier effect is there, and as well as what I can call means diode resistance must be limited you can call. So ideal thing is only just theoretical only, practically only you can consider that practical diode only, this one. Okay, this is just an ideal approach where the barrier effect is 0 and the diode resistance is what means unlimited you can call. Now I can able to discuss what are the equivalent model of the diode, both for ideal condition and practical condition you can check out. See, so now I can able to go for equivalent model of a PN diode. Equivalent model of a diode I go. So both for ideal condition and practical condition I can able to examine now. First case now I can able to go for ideal condition. So already I told that for ideal condition the barrier effect is 0 and as well as the diode resistance is unlimited. Based on that, in the case of ideal condition, the diode just look like as a switching element you can call. So this is the equivalent model of a diode. This is anode. This is the cathode you can call. Diode just act as a switch. And a forward bias, it acts as a closed switch. And a reverse bias, it acts as an open switch you can call. In forward bias, it acts as a closed switch of 0 resistance. In reverse bias, it acts as an open switch of infinite resistance you can call. Now I can able to go for practical condition now. So this is the practical condition of a diode. Practical model I go. According to the practical model, what you say means diode as a switch, diode considered as a switch. Along that, it can also have a barrier effect, right? That is a barrier potential is there. That is always be directed from anode to cathode you can call. So this is the internal barrier voltage. And as well as it also have some resistance. So because of the diode is a non-linear, dynamic or AC resistance only taken, that is this one R. R should be the AC resistance you can call. So this is the equivalent model of a diode. This is anode, this will be the cathode, and this will be the barrier potential or cut-in voltage you can call. VBA or VR you say. That is due to barrier effect you can call. This is about 0.3 volt for germanium and 0.7 volt for silicon. R stands for what means AC resistance you can call, that is called as a dynamic resistance. AC resistance you can call. Because of the diode is a non-linear, dynamic resistance is valid. So diode, if it is a linear, then you can able to use a static resistance. But a diode is not be a linear device. It is a non-linear where dynamic resistance or AC resistance only considered you can call. So all this is the internal model of a diode you can call. All this will be the internal model of a PN diode. So this thing completely the internal model of a diode, right? So here in the ideal condition, this barrier potential is 0, and for ideal condition, dynamic resistance is unlimited you can call, that will not be permitted there. So this is the equivalent model of a diode of practical. Now in this practical model, both DC and AC terms are there. Now can able to rewrite what is the approximate DC model and approximate AC model of a diode you can call. Now I can able to go for approximate DC model that can be used in the DC circuits. So this is the approx DC model now I go. So in the case of DC model, only DC conditions you can take and ignore that dynamic resistance you can call, right? In the DC model only can able to take what means DC conditions and that AC resistance will be ignored there. Then what is that equivalent model means? Like this it comes. So this is anode, this will be the cathode. So this is the barrier potential, which is always be an opposing potential and forward bias you can call. So whose the direction always from anode to cathode I say. So this value is nothing but VBI or VR. VBI or VR, you know, that is a cut-in voltage which is about 0.3 volt for germanium or 0.7 volt for silicon you can call. So this is the equivalent approximate model of PN diode you can call. Okay, in DC condition. Now I can able to go for approximate AC model now. Approximate AC model now I come back. Okay. In the AC model, only AC conditions are you are accepting now. So based on that, what it is means, here barrier potential is ignored, the dynamic resistance will be taken, then the equivalent model may come like this. So this is the diode as a switch. Okay, this is the resistance. So this is the equivalent model of a diode under AC condition you say, where R stands for dynamic resistance. And remember now, this resistance will be valid to use whenever the switch is closed. That switch commonly closed in forward bias, so that in PN diode, forward resistance is most valid you can call. And if you calculate that one now, what is that forward forward dynamic resistance means like this you say, R equal to eta Vt by I ohms. R equal to what sir means eta Vt by I, where eta stands for ideality factor, Vt stands for thermal voltage, and I stands for current in forward bias you can call. So this resistance is valid to use whenever the switch is closed. I told that switch is commonly closed in forward bias. Based on that, the dynamic resistance of a diode commonly considered in forward bias mode, where I stands for DC current of forward bias. You are calculating the AC resistance in terms of DC bias current you say. That is most valid to use in amplifier circuits. So what are the different terms there you say, where eta is nothing but what I can call. So where eta stands for ideality factor I can call. So where eta is what you say, ideality factor. Eta is ideality factor I call. That is commonly considered 1 or 2. 1 considered for germanium, 2 considered for silicon. Okay. So commonly it is considered to be what means. So higher conductivity means lower value, lower conductivity means higher value. If I compare germanium to silicon, germanium conductivity more taken as a 1, silicon conductivity less taken as a 2 you say, right? And what is that Vt means? Vt stands for thermal voltage you can call. So Vt equal to Kt by Q, where K is a Boltzmann constant, T is the temperature in degree Kelvin, Q is the charge. So Kt by Q, substituting K and Q, that is T by 11,600 volt you can call. And at room temperature of 300 degree Kelvin, it is a 26 millivolt. At T equal to 300 degree Kelvin, Vt equal to how much means 26 millivolt you can call. And what is that I means? I should be the forward bias current you say, current in forward bias. That is a DC current you can call. So you calculate the AC resistance in terms of the forward bias current you can call, so that the dynamic resistance of a PN diode varies inversely with this forward bias current you can call. So this is the approximate DC model. Here this is the approximate AC model. This is the complete equivalent practical model of a diode I told. So in the case of ideal condition, you know that barrier effect is 0, and as well as resistance is unlimited, that are not be considered in the equivalent model of ideal. Okay. Now, how do you know in a given circuit the diode is on or off means? Now I can able to examine the testing of a diode whether it is on or off. Let us see these things what it is. So testing of the diode, now I can go. So testing of a diode. So when it is on, when it is off I can call. So when the diode should be on means whenever I told that anode potential should be greater than or equal to cathode potential you can call. Otherwise, so difference between anode and cathode potential must be greater than the cut-in voltage. See this one now? This is the condition of on. Diode should be on if, so the difference potential, that is anode minus cathode potential you can call greater than the cut-in voltage for practical case, right? If it is ideal case means cut-in voltage is there, you can take 0. So diode should be on if the difference potential between anode and cathode should be greater than VR. VR means cut-in voltage you can call. For ideal case, cut-in voltage to be taken as a 0, you say. So diode should be off. Diode should be off if the difference potential, that is VA minus VK, less than or equal to VR. So if ideal condition you taken, then VR should be 0 there. Means there VA less than or equal to VK you can call. So condition for on, condition for off you can call. And now you can also use the short circuit test and open circuit test for the diode to know whether it is on or off. So what is that, the short circuit test and open circuit test, now you can able to go. So AC means short circuit test and OC means open circuit test we can call. So AC and OC test for a diode, now I can go. So using which in a given circuit you can identify the diode to be either on or off you can call. Short circuit test, other one is what? Open circuit test you can call. So first of that one, now I can able to go for short circuit test. Now I can able to go. First of this one, now we can examine the short circuit test, AC test. So in this one, what you can assume means, so the given PN diode to be act as a short circuit. This is the given diode, I say. So this diode is assumed to be as a short circuit, you can call like this. Diode to be short circuited. So in this short circuit diode, calculate the current from anode to cathode. Calculate the current from anode to cathode you can call. And so now, so short circuit test, now I can able to go. Assume the given diode is just shorted now, and there you can able to calculate the current. Suppose what is the current you calculated from anode to cathode? If current, what are the thing you calculated from anode to cathode is greater than 0, diode is on. On means forward bias. Suppose if I less than 0, that is current should be negative condition you can call, then diode should be off state you can call. Understand this? So assume that diode is a short circuit, and then you can identify the current from anode to cathode. If the current identified to be greater than 0, diode should be in the on state, and if the current should be less than 0, the diode to be off state you can call. Suppose if the number of diodes connected in parallel, so number of diodes are connected in parallel in a given circuit, the short circuit test is not be useful now. Short circuit test must be invalid at that time. Suppose it is only one diode, no problem. Suppose if the number of diodes connected more, in a given circuit and that to be in parallel, at that time this short circuit test to be invalid, I told. So short circuit test should be invalid if the number of diodes connected in a given circuit should be more than one and they are in parallel. Under such condition, the mostly used is what, sir, means open circuit test. So most frequently are using OC test now. That is called what means open circuit test. So this one now. What is this OC test means? I can able to go for OC test. OC test stands for what, sir, means open circuit test you can call. In this OC test, what is the thing you can call means the given diode considered as a open. This is one. This is the diode I call anode, cathode I say. So the given diode should be open body. Now I say this is the open body. Diode considered as a open. Okay, anode, cathode. Here I assume that this node potential is VA, this node potential is VK I can call, right? So anode node potential is VA, cathode node potential I can call as a VK I can call. So assuming the diode as a open, there you can able to check out if VA minus VK greater than VR. Okay, so if ideal case means that VR to be 0 there, again I told. VA minus VK greater than VR, diode to be on, right? If VA minus VK less than or equal to VR, diode should be off state. So diode is on if VA minus VK greater than VR, diode should be off if VA minus VK less than or equal to VR you can call. Consider these conditions. Suppose if the number of diodes are connected in parallel, and having the same cut-in voltage VR, then which diode can conduct first means, right, the diode which have more VAK, that is more anode to cathode potential, can conduct first. Understand? So what I say means, the number of diodes are connected in parallel, not only one diode, more number of diodes are connected in parallel and having same cut-in voltage, right, for all diodes, so the cut-in voltage is same. Then among that, which diode can conduct earlier than other means, whatever the diode who can have more anode to cathode potential, that is more VAK, can conduct first. After that, you can examine for the other diodes by calculating their VAK to say whether they are on or off. So who to be conducting earlier than other means, the diode which have more VAK, right, that can conduct first if all diodes maintain the same cut-in voltage. Okay, this is one of the case I say. And one more thing you see, now the number of diodes are connected in parallel with different cut-in voltage, not same cut-in voltage, then which of the diode can conduct first means, what is the diode which has a lower cut-in voltage, that can conduct first. That's my options. Okay, so first one I say what? If the number of diodes, right, connected in parallel with same cut-in voltage, means cut-in voltage for all diodes is same, then which one conduct first among that means, then the diode that has more VAK, that is anode to cathode potential is high, right? Diode which has more VAK can conduct first, than other. So this is one of the case you go. What are the diode which has more VAK that can conduct first, you say. So one more thing you can able to go, one more option I say, if the number of diodes connected in parallel with different cut-in voltage, I call. What is that cut-in voltage means, you know, VR. Then who can conduct first means, then the diode that has low value of VR, can conduct first. Confirm? So if the number of diodes that are connected in parallel with a different cut-in voltage, you can call, what are the diode which has a less value of cut-in voltage that can able to conduct first, I told. In the previous case, what are the diodes which have the same cut-in voltage, then who can able to conduct first means among those diodes which have a more VAK that can conduct first. Now I can able to check out some examples based on this. now. See, so now suppose I given a question like this. So I take some circuit. This is 1K. This is some supply voltage of 5 volt I taken. Here two diodes I given. Both are in parallel, but made of different material I say. Suppose this is a D1 made of germanium, whose cut-in voltage I can call some 0.3 volt. The cut-in voltage for that D1 I call 0.3. This is one more diode made by silicon, I assume, okay, whose cut-in voltage Now I can assume as a 0.7 volt. Okay, two diodes I given. For the first diode, the cut-in voltage 0.3. For the second diode, I consider that cut-in voltage 0.7 volt. And applied with some supply of 5 volt, I can call through a resistance of 1 kilo ohm. I ask that which of the diode is on there. Which of the diode is on? Among this one, which of the diode is on? The options I given like this: D1 only, D2 only, both, D1 and D2. Okay, none of these I call. So which one I ask? Say that means either D1 only on or D2 only on, or both D1 and D2 on. None of this I call. Let us see this one now. Originally, if I check out that one now, for both the diodes, their anode is kept positive with respect to cathode there. This is the anode of D1. This is the cathode of D1. This is the anode of D2. This is the cathode of D2. For both of that, anode is positive with respect to cathode. Commonly you say that forward bias both. But you observe now, here both the diodes are connected in parallel. Both do not have the same cut-in voltage. Both have the different cut-in voltage. Then who to be conducting earlier than other means first to D1 conduct. So among this one now, so because the D1 cut-in voltage is less, according to the condition I say, who conduct earlier means D1 conduct earlier than D2, right? So for D1 the cut-in voltage is less, so that who to be conducting first means D1. See this one now? So D1, conduct earlier, I say D1 conduct earlier than D2, I say. How do you say this? D1 conduct earlier than D2 means because whose cut-in voltage than compared D2 is less, so that D1 conduct earlier than compared towards her means D1 conduct earlier than what means D2 you say. So D1 going to be conduct earlier than D2 now. Let us see this one now. If I can make that one like, so what happened here, you see this one now. So D1 I can able to make to be on. What happens, see this one now in this. So this is 1K. This is 5 volt. Okay. D1 on you can call on. So having a barrier potential is what means directed from anode to cathode, that is 0.3 volt. This is the D1 equivalent model because it is on, you know. This is the D1 you can call. Now what about D2 you can able to go. This is a D2 now. This is a D2 whose cut-in voltage is 0.7 volt you can call. Observe now both D1 and D2 are in parallel. So according to the parallel circuit condition, the voltage across each is same. So already this path containing the voltage is 0.3. Then maximum voltage across D2 become 0.3 volt only. So maximum voltage across D2 is 0.3 volt only. Means for D2, the corresponding anode to cathode voltage less than its VR. So what is the anode to cathode voltage for D2 means just 0.3 volt only. So whose cut-in voltage how much means 0.7 you can call, right? So for D2 you say this. For D2, you see this one now. Anode to cathode voltage according to the parallel circuit principle, how much means that is just 0.3 volt. So that means for D2, what you can call means the corresponding anode to cathode voltage less than its cut-in voltage of 0.7 volt. This is 0.7 volt for D2 you can call. So based on that, D2 should be in the off state. So who to be on means D1 to be on. So here the person who to be on means D1 on and D2 should be off. Both do not be on, only one to be on, that is a D1. Why sir means D1 conduct? Why D1 conduct earlier means because its cut-in voltage less than D2 who become on. Once it is on, the maximum voltage across D1 is just 0.3 volt and which is appeared in parallel with the D2, and then based on that the voltage across D2 never cross 0.3 volt you can call. So that voltage drop now look like me less than the cut-in voltage for D2. So D2 should be off state. So who to be on means only answer is D1 only, right? And so now this.